Thank you, Piero. So I'm showing the result on the development of a novel research platform for ultrasound research. So what's the motivation that drove us to develop a new research scanner? So we wanted to have full flexibility, especially on transmission, wave generation. That means full control on the transmission on the array, and full flexibility on deciding on transmit and receiving strategies and elaboration modules, and also flexibility on real-time display, real-time elaboration, and especially data storage, which is very important for research. And then also the probe connection is a problem to be solved because we wanted to be compatible with as most probe as possible. And on the channel number point of view, obviously we wanted to have a high channel number, but we also ended up to understand that we need some kind of modularity, and also channel count couldn't be so high because we also wanted to stay within a reasonable cable size, and also we wanted to be compatible again with the small matrix array, which uses small cables again. And last point, which is counteracting the previous, is also we wanted to have a small system to be portable, since we aim to share the system with the research community, so we need to have portability. So based on that, we decided at the end to start with a 256 channel system, which is a reasonable compromise. And the system is organized mainly in a ring of boards which are arranged on a back plane, and each board can manage 32 channels. And the boards are connected one each other through a double serial rapid I/O connection, which brings 40 gigabit per second per branch. And we studied, and we ended up with a solution for probe connection. And we have, on the back plane, we have another probe connector, which is easily replaceable, and we can interchange between different probe adapters. One special board is a user interface board, which manages the connection, digital connection to the external world. And I start from this board. The board has USB 3, the main connection for the system is a USB 3 connection that can handle a real transfer rate of 300 megabytes per second. And with this connection, we can interact with the PC software, which controls the system and display the real-time elaborated data. But on the system-on-chip FPGA, which we have on the board, we implemented also a Linux operating system, which can use the Ethernet connection, which is here. And in this way, we can also remotely control the system from any point of the internet. So the board is connected internally through a serial rapid I/O switch, which brings a total of 80 gigabit per second of bandwidth to the ring. I say 80, it was 40 before, because there are 2 branches for each board, and each branch has 40 gigabit per second. And we also host here one multi-core DSP, which hosts 8 cores at 1.2 gigahertz. And this DSP is in charge of performing custom application modules. And also it is in charge to stream the data to the PC, showing real-time elaborated data. And now we switch on the 32-channel front-end module. On this module, we start on here from the analog side. We have all the electronics to drive and to receive for 32 channels. And in particular, we implemented 32 arbitrary waveform generator for the transmission side. And we also have the 32 A to D converters running at 80 megasample per second at 12 bits. We have one FPGA here, which is in charge of beamforming the receiving data and to store the raw sample data. The FPGA can implement up to 8 parallel beamformers, and the total beamforming capability of each of these FPGA is about 1.8 gigasample per second, which is a nice number. And it has also 2 gigabytes of DDR3 memory for storing the beamforming instruction. Then, also here, we have a couple of multi-core DSP. So in this case, we have 16 cores in total. And they are in charge of custom elaborating the raw beamformed data coming from the FPGA and to stream the data toward the user interface board, where they will be again elaborated and streamed out. Again, the connection. So the system is the same, it's guaranteed by a serial rapid I/O switch. So that's the board. We use the 32-channel front-end board, and we can see here the 2 DSPs with space for memory modules. Each DSP has 4 gigabytes of DDR3 memory. It stays here. This is the beamforming FPGA, the A to D converters, and the serial rapid I/O switch. What you don't see here is the transmitter section. That's because it is hosted on top of the FPGA on a piggyback board. And we decided that this solution, both for space and also for flexibility again, and we can choose to have 2 different implementations. One is a simple 3-level square wave transmitter, simple transmitters. And the other solution that we actually implemented is to use high voltage linear amplifier that are capable of driving up to 200 volts peak to peak. So on the system we will have 256 channels of linear transmitters at high voltage. And now I start to show you the results on that. So we start from the performances of the linear amplifier, and this is a test with the linear frequency modulated chirp, where we pulsed frequencies from 5 to 12 megahertz with Taki tapering, and this is the time domain and frequency domain results. You can see the good flatness in band and low distortion, acceptable distortion in outside band. And the pulse amplitude was, in this case, 80 volts peak to peak. And now I show you the results on the use of the full system. And we show here a simple high frame rate application. The setup was to fire one unsteered plane wave. And the system has been configured to make one full frame beamforming for each transmitted plane wave. And also the system is configured to store up to 1,000 full frames, beamformed full frames. And the results were that we were able to beamform up to 700 frames per second, slightly more, using one single beamformer inside the FPGA. And since we can go up to 8 beamformers, you can scale up the performances when we will have finished the test, obviously. And also, this frame rate can also be scaled up with frame dimension, as you probably know. And also, a good result is that we were also able to do a real-time display of the region of interest, taking a subset from the high frame rate beamformed data. Obviously, the real-time display was not at high frame rate because it makes no sense of showing 700 frames per second. And so, this is one example of a high frame rate acquisition. And in this case, we got 600 frames per second, and we are playing back at 30. This is a femoral vein with a valve, and you can appreciate the time resolution on the valve dynamic. And if the projector helps, you can probably see the scattering of the blood vessels of blood cells when the valves open. And that's how the system will appear once we design, once we build a proper case. Just to give you a report on the dimension, it's roughly a cube of 30 centimeters per each side. And so, since now we have one system that is 256 channels, we also started on the same time the design of a small array, a small matrix array. I say small because it is 256 elements, but that's a sparse array using a layout, a spiral layout, and this work, and also based on CMAT technology, and this work has been carried out in collaboration with the group of Roma 3. And what's going on again, now that we have the system, we also have yet a software that is working in a compatible mode with the previous system. We have to implement some kind of modes that are more related to the new capability of the system, like let's say, retrospective iframe rate or real-time vector Doppler. And when we will have the probe, I hope in a few months, also 3D real-time imaging. Thank you very much.